Morgan Cable is, as you know, from my announcement, working at the Jet Propulsion Laboratory in Pasadena in California. And she is also the science lead for the Exobiology Extant Life Surveyor. And Morgan has always been very much involved in different space missions, that is including the Cassini mission. She's a co-investigator of the Dragonfly mission and also is very deeply involved in the Europa Clipper mission. So she has been doing a lot of work in exploring other planets and their satellites. And her own research focuses on organic and biomarker marker detection strategies. This includes both in situ and remote techniques. She has been also a very keen participant in our activities at the Nordic Network of Astrobiology and the European Astrobiology Institute, and also co-led a team of investigators exploring the colonization of lava fields in Iceland, which I had also the honor to participate a couple of times. Many thanks, Morgan, for coming, and I will conclude my presentation now, and the floor is yours.
Thank you so much, Wolf. It's such a pleasure to be here today. Thank you all, and many thanks to Wolf and the European Astrobiology Institute for welcoming me. So let me go ahead and share my screen, and let's get started. So I'm going to give a bit of a whirlwind tour of a few things that we're working on at NASA in collaboration with our European partners and other scientists from across the world to explore certain parts of our solar system that we call ocean worlds. And I think it's appropriate to start by defining what that is. Now, of course, you may think, well, Earth is a perfect example of an ocean world. It is a world, we have oceans, box checked. But what we're finding is that Earth, as we explore our solar system, seems to be more the exception than the rule. And by that, I mean that Earth has its liquid water oceans on its surface. Most of these other ocean worlds that I'll be telling you about today tend to have a liquid layer. Almost always it's liquid water, but it doesn't tend to be on the surface. Instead, this tends to be underneath a layer of ice. Now, sometimes that liquid water ocean is in contact with the rocky interior of the moon. Sometimes there may be a layer of high pressure ice in between that water and the rock. And we'll talk about why that's important from a habitability standpoint. But so far, we found many different examples of these types of ocean worlds. These are just a few here. I don't have time to talk about all of them today, so I've just selected 3. So bear with me if one of your favorites isn't one that I'm able to touch on today, but all of them are worthy of study. These are fascinating worlds. And by exploring each of them, we can get an understanding of the spectrum of habitability, places where we find the ingredients for life as we know it, to see if indeed we are alone in our cosmic backyard. So first, let's skip over to Jupiter. So we've just traveled 4 astronomical units away from Earth. This is one of the amazing images that was collected by, I think this was collected by the Juno mission, but Galileo has also collected some really incredible images throughout its time in the Jovian system. This is one of my favorites. This is one of the moons of Jupiter, Europa. And one of the things that you may notice about this icy surface, this is a water ice surface, it has some coloration. We're still exploring what that composition could be. It could be salts, it could be organics, it could be a mixture of both. But one thing you may notice about Europa's surface is that it doesn't seem to have many craters. And that's actually something that's important when it comes to potential habitability. Craters are a way that we are able to date surfaces. Typically, the more craters you have on a surface, the older it is. And so the fact that Europa is missing a lot of craters tells us that it must be very young, on the order of, depending on who you talk to, maybe 50 to 90 million years. So this tells us that something must be refreshing that surface. Now, if we take a slice through Europa and look underneath, we have evidence from the Galileo mission, as well as other observations that tell us that Europa has a global subsurface liquid water ocean. And we believe, based on our observations and density and gravity measurements, that that ocean is in contact with a rocky interior. Now, that'll be important in a moment. I'll talk about that a bit more. But one of the key ingredients that we look for when we're trying to understand if a world has the conditions for life as we know it is liquid water. And compared to Earth, Europa actually has more water by volume, about 2 times all of our oceans combined. So this is one of the reasons why this is a primary target for exploration, because it does seem to have this key ingredient as well as others. Now, you may ask yourself, well, we are 5 astronomical units away from the sun. It's much colder out here in the outer planets of the solar system. So how the heck does this water stay liquid? Well, that has to do with Europa's orbit around Jupiter. Jupiter is a very large planet. It's got a strong gravitational pull, and Europa's orbit is not perfectly circular. So what that means is as Europa orbits in its about 3.5-day cycle around Jupiter, at some points, it will experience a greater gravitational pull, and at some points, it'll experience less. And that leads to something that we call tidal flexing, which generates enough friction that we think this is one of the key reasons why Europa's ocean stays liquid. There may also be some heating from the decay of radioactive elements in Europa's core as well. We call that radiogenic heating. And we think that it's a combination of these two forces that are leading to this ocean staying liquid, presumably for a very long amount of time. And this is important because that heating could lead to an environment like this at the ocean floor. Now, this is not Europa. I wish it was. This is Earth, at Earth's seafloor at the Mid-Atlantic Ridge. This is an example of a hydrothermal vent. This is a place where water is heated up by Earth's interior, and then when that heated water, it picks up some minerals, and then when it gets conveyed out through cracks and conduits into the colder ocean waters, those minerals precipitate, and you end up with a lot of chemical and thermal gradients, things that life can take advantage of. And what you can see here is it's not just microbial life that can live off this geothermal, this hydrothermal energy, but crabs and shrimp and all sorts of organisms living in an ecosystem. And so these are the kinds of examples of ecosystems on Earth that are as far removed from sunlight as possible, that are living off of very similar energetic contributors to what we might think might be at the seafloor of Europa. And so Europa seems to have all 3 ingredients for life as we know it. It has liquid water, it has an energy source based on this hydrothermal energy that we think is keeping that ocean liquid, and that interaction between liquid water and the rocky interior allows for some chemical energy to be able to be utilized by organisms. And it also seems to have the chemical building blocks for life as we know it. We think that it has organic molecules very similar to what we see in meteorites that could be utilized by life. So it has all of these 3 things. But how might we search for evidence of life if indeed there is some in the ocean? Well, we do have evidence that Europa's surface is young, and there are different processes. This is just one example of ductile ice being able to move material from the interior of Europa up to its surface as bands spread open and pull up some of that material from Europa's interior. And so there are some processes like this, similar to like diapurism here on Earth. There could be near surface reservoirs that are also generated by some localized heating that then could lead to plume activity. We've had some tentative evidence of some potential plume activity on Europa that hasn't been verified yet. That's one of the goals of the Europa Clipper mission. But we do see places where it looks like the surface has been disturbed in chaos terrain and regions like this that could hold evidence of what the composition of Europa's ocean is. And if indeed there is life there, potential biomarkers. And so these are some things that we really want to study. And we're doing that with the Europa Clipper mission that is being built right now. I just saw it the other day in our clean room here at the Jet Propulsion Lab. All of the instruments are integrated, which means that they have been bolted onto the spacecraft, which you can see here. The solar panels aren't on yet, but they will be put on in short order, and that's how this spacecraft will get its power. So it will be able to, recharge at every orbit and be able to utilize instruments during flybys of Europa. So we're not orbiting, we're actually going to be orbiting Jupiter and doing close flybys of Europa. And we'll be bringing our full instrument suite to bear during each of those encounters. We have two different classes, two different categories of instruments here. Some that we refer to as remote sensing. So these will look at light and other, different wavelengths and different regimes of the electromagnetic spectrum and how that can tell us about the surface composition of Europa as well as its interior. And then we have some in situ instruments. These will either be measuring the plasma environment or the magnetic field, or things that are outgassing or particles that are sputtered off of the surface of Europa. So we'll basically be able to get a taste of what Europa's surface is made of. And this is an example sped up of what one of those flybys might look like. The nice thing about these flybys is that we're able to operate instruments in a very intricate dance, carefully choreographed, where we start by taking some measurements from a bit further away, some global images, and are able to then, as we get closer, get much higher resolution images and use some of those in situ instruments that require very close proximity. For example, if we're measuring the gases that are being emitted from Europa, or some of the grains that have been sputtered off of the surface by micrometeoroid impacts. And so this just gives you an idea of the complex sequence of planning that goes into each encounter of Europa. And the goal of this mission is to be able to use all of these data sets from these instruments in conjunction to be able to form a more comprehensive picture of what Europa is made of, its potential habitability. Indeed, if there are certain types of biosignatures, this payload would be sensitive to those. Now, this is sped up, but again, you can see that the closest approach part of our encounters are still pretty quick. So we have a lot of very experienced engineers that have built off of experience from other missions like Cassini that did these kinds of encounters in the Saturn system. So if you'd like to learn more, I encourage you to go to europa.nasa.gov and learn more. We're also on Facebook, and we have a live view of the clean room at JPL where this spacecraft is being assembled that you can log on through that europa.nasa.gov page. There's a link there, and you can see some of our engineers at work. But at JPL, the Jet Propulsion Lab, we dare mighty things, and we're always thinking about what might come next. So Europa Clipper is going to unveil a whole host of new bits of knowledge and inspire new questions about Europa, but it's not going to land. And there are certain questions that you really can benefit from having a platform that is touching the surface, that is collecting large amounts of carefully selected samples. And so we've developed over the last few years a Europa lander concept. This could also go to other ocean worlds, like Enceladus, for example. It's got very special designed hardware that's meant for cryogenic ice. Cryogenic ice, very cold ice, is different from the ice in your freezer. It has properties in some cases that are much more similar to granite than water ice. And so we needed to develop special tools to be able to cut into the surface, collect a sample without chemically changing it. We don't want to modify something and then say that a certain molecule, for example, is there when that was due to chemistry during the sampling process. And so this type of a lander would presumably have a payload that could search for different biosignatures or make other detailed compositional measurements of the surface, things that wouldn't be possible from flyby or orbit. Okay, so that's one ocean world. Now let's skip another 5 AU. So the distance from the sun to Jupiter, we have just done that again to get to Saturn. Space is big. This is one of my favorite images of the Cassini mission that explored Saturn, its moons, and its rings for about 13 years. It was a real privilege to be involved in that mission. I was only involved for the last few years, but it was such an incredible team and an amazing set of discoveries. And one of them was about this moon, the largest moon of Saturn, that you can see to scale. This is a single image right here. It's a rather large moon called Titan. Let's zoom in here. This is actually what it looks like in the visible. Titan is larger than our moon. It's actually, if you count its atmosphere, the largest moon in the solar system. If you strip its atmosphere away, then Jupiter's moon, Ganymede, gets a win. And you know what? That's fine because Titan is so fascinating. It doesn't need that accolade along with many others. Titan has an atmosphere. It's thicker than Earth's atmosphere, about 1.5 times thicker. Like our atmosphere, it's nitrogen rich, but it also has some methane. And not only does it have methane in its atmosphere, but it has methane on its surface. This is one of my favorite images taken by Cassini. This is taken in infrared wavelengths. And what you can see here is a glint off of something in the North Pole. This is actually a specular reflection, just like if you were in an airplane and you looked down on a sunny day at a lake and you saw sunlight glinting off of that smooth surface of the lake. That's exactly what you're seeing here, just in wavelengths that your eyes are not sensitive to. But this was some of the definitive proof that we have that Titan indeed has liquid on its surface. But in this case, it's not water. So Titan is familiar in a lot of ways to Earth and yet very alien. It has a thick atmosphere, it has clouds, but unlike the clouds on Earth, which are made out of water vapor, here it's made out of hydrocarbons, methane and ethane, that rain down and form rivers just like we have here on Earth, except they're made out of different stuff. And they're carving channels out of different stuff. We're not sure exactly what the surface of Titan is made of. Its atmosphere has methane, which absorbs very strongly in a lot of the wavelengths we might use to determine composition of a surface. So we're essentially blind from orbit to what Titan is made of. We really need to get down to that surface to find out more. Titan, as I said, has these lakes and seas, but these are made out of liquid methane, ethane, and a little bit of propane. And they're quite large, on the order of, hundreds of square kilometers. And for contrast, since I was giving a talk to you all, my European colleagues, I figured I would find a good example. This is the largest lake in the EU, in Sweden, Lake Vänern, and apologies if I have mispronounced that, but you can see the sheer scale is very different. Titan's lakes and seas are quite large. Titan also has dunes similar to Earth, but again, look at the scale bar. The scales are different here, and we think that they are made of different stuff. On Earth, dunes are typically made out of sand or gypsum or silica-based particles, but on Titan, they could very well be made out of organic molecules. One thing that we found is that there is chemistry happening in the atmosphere. That's what leads to it being so obscure in visible wavelengths. Titan has haze layers in its atmosphere that are formed by photochemistry. So light or very rapidly accelerated protons and electrons that are from the solar wind that Saturn whips around with its magnetic field. They slam into these nitrogen and methane molecules in Titan's atmosphere and form all sorts of complex organic molecules. Pretty much any combination of carbon, hydrogen, and nitrogen you can think of probably exists on Titan from these chemical processes happening in the atmosphere. And so those we think are essentially snowing down on the surface and making this veneer of organic rich material. But underneath that, we have a water ice crust, just like Europa, just like a lot of other ocean worlds. And then underneath that, a liquid water ocean. So Titan is unique in that it actually has two liquid phases, hydrocarbons on the surface and liquid water inside. And boy, wouldn't it be interesting to, say, stand on the shore of a Titan lake and ponder what sort of primordial chemistry could be happening in those hydrocarbon liquids, or to be able to explore the rest of Titan's surface. And luckily, we are doing just that. This is the Dragonfly mission, which is currently starting Phase C activities. It's led by the Applied Physics Lab at Johns Hopkins University, but has collaborators from, including myself and others from JPL and all across the US and Europe. This is an 8-bladed helicopter, which we like to refer to as a relocatable lander, because Titan's gravity is much less than Earth and its atmosphere is denser. It's actually easier to move across the surface in these flying hops than it would be to drive like a traditional rover. So this enables us to explore a lot of different parts of Titan's surface in a relatively short amount of time. We're baselining only a couple of years of exploration for our prime mission. Now, you may notice that this lander doesn't have an orbital phase. It, direct to Earth, is able to contact and transmit data through its high gain antenna that you saw going up and down during that animation. And while it does spend most of its time on the surface, Dragonfly can also make measurements while it's in flight. This is most important for our meteorology contingent of our team. Now, where are we landing? Well, after a lot of debate and discussion, we decided instead of going to the poles, that it would be more instructive for us to land in this equatorial region of Titan. We selected Selk Crater, or an area nearby Selk Crater, because this allows a lot of different access to different terrain types. Now, I had mentioned a few of those earlier, that Titan has dunes, it has lakes, it has rivers, and all sorts of things like that. And the nice thing about craters is that they are a natural way of excavating that veneer of what we think is organic material so that we can look at essentially the bedrock of Titan, which we think is water ice. And so by landing near this crater, we get access to the inner bits of Titan as well as some of those dunes and interdunes. And it gives us a really nice cross section of what we think Titan is made of. Now, when it comes to Dragonfly's exploration strategy, we have a way of essentially scoping out a new candidate landing site each time we take off, and then going back to a spot that we have deemed safe already in a previous flight. And so this allows us to have scientists and engineers in the loop here on Earth to be able to survey that site, make sure that it's safe from, an engineering perspective, that it meets our criteria for a safe landing site, and B, most important to me, I think, is that it's scientifically compelling. Is there something new, something exciting about that site that would make us want to land there and study it further? And when we do land, Dragonfly has a sampling system called Draco, which is essentially a percussive drill linked to a fancy vacuum cleaner, because Titan has an atmosphere, so we can use that to our advantage. It's able to break up material on the surface, suck it up, and deposit it into two different kinds of sample cups. One you're looking at here, we can do laser desorption ionization. This helps us get at fragile organic molecules, things like fatty acids, which you're seeing here. As well, we have sample cups that are designed for a gas chromatography kind of analysis, where here we will heat up the sample cup doing pyrolysis, so that releases all sorts of volatiles. And then those pass through a column that could separate, for example, chiral sets of amino acids. This is one of the different indicators of biosignatures, right? That if you have only one-handedness of amino acids present, where in an abiotic case, you would expect an equal mixture. So if indeed there are some biosignatures like that on the surface, the Dragonfly mass spectrometer would be sensitive to them. And there's a whole other host of instruments aboard this amazing relocatable lander, including a gamma ray and neutron spectrometer, a meteorology package, and an imager. And so I encourage you to go to the website below to learn more about this amazing mission. All right, so we've talked about two ocean worlds so far, Europa and Titan, that we are sending missions to that are in development right now. But let's talk about one world that we studied a lot with Cassini and right now has some missions proposed, but nothing solid on the books yet. And that is Enceladus. This is another world of Saturn. And again, this is one of my most favorite images that Cassini took of this tiny moon. Small things can be mighty, and Enceladus certainly is no exception. And you can see this beautiful plume of material that's coming out of the South Pole. If we zoom in further on the South Pole, you can see these four large fissures, these cracks that we refer to as the tiger stripes. They're on the order of 120, 130 kilometers long. They're about 35 kilometers apart. And out of these fissures, that's where this material is coming that forms this plume. And we have evidence that this material is sourced from a global subsurface liquid water ocean, just like on Europa, just like on Titan. But thanks to these cracks in the South Pole of Enceladus, we have a unique opportunity here. This is the one place where we can collect material from that ocean without the need to dig or drill. So this gives us some unique opportunities to ask some compositional, some potentially astrobiology questions about what might be lying beneath, lurking within that ocean. Now, Cassini flew through the plume of Enceladus multiple times, but it wasn't meant to be a life search mission. It didn't have instruments on its payload meant to look for biomolecules, but it did give us some tantalizing evidence that makes us want to go back. For example, there was one instrument on board that was called INMS, the Ion and Neutral Mass Spectrometer. This instrument measured the gas, the vapor phase of that plume. And we found that it was rich in water. Duh. Yep, makes sense. But also some other molecules that got us interested. Things like methane, hydrogen gas, H2, and simple and complex organic molecules. Now, complex, I have to use carefully here because this instrument had a mass cutoff of about 100 Daltons. Here's an example of a mass spectrum, and this one even doesn't even go that high, only to 80 Daltons. Now, for a sort of calibration for you, the smallest amino acid, one of the building blocks of our proteins that make up our cells, the smallest one, glycine, is mass 75. Many of the other amino acids and of course the proteins that they make up are much, much larger than that. And this instrument wasn't designed to look for those. But again, we do see these small organic molecules, these precursors, and also things that life either eats or essentially, breathes out or poops out, things like methane and hydrogen, which got us excited. So that's in the gas. What about these ice grains? So we not only see gas in the plume, we see grains that we believe are water droplets that froze once they reached the vacuum of space. And here again, we saw some tantalizing evidence. This was measurements that are made by a dust detector called CDA, the Cosmic Dust Analyzer. And again, this was not designed to look for biomolecules, but it did find a whole host of organic molecules, things that we call high mass organic cations. And you can see them sort of here in this mass spectrum. But the way this instrument works, it's a time of flight mass spectrometer. And so as you get to longer times of flights, as molecules take longer to reach the detector, your resolution decreases. So it's harder to distinguish between species of similar mass. So again, this instrument gave us some tantalizing evidence, but this wasn't designed to look for life. It just tells us that a lot of the building blocks for life as we know it are there. Not only are the building blocks there, but we also have some estimate of whether or not hydrothermal activity could be happening. So we found primarily in the E ring, which is a ring around Saturn that Enceladus is forming from its plume materials that are coming out of its south pole. We found these silica nanograins, and these certain type of silica, the fact that it's SiO2, not SiO4, and a radius of about 2 to 9 nanometers. The only way that we have found that you can make these kinds of grains is if you have liquid water in contact with a rocky core at temperatures of 90 degrees C or above. And since you're all from Europe, you work in Celsius, so I don't need to convert any of that to Fahrenheit, but that's quite warm, right? That's quite hot. And this gives us an idea that there could be hydrothermal activity down in that seafloor. And so this is, of course, really exciting for us. The Onion is sort of a parody newspaper, but was building off of some data sets that we've recently compiled together that tell us that, yes, Enceladus does seem to have all of the ingredients for life as we know it. And in fact, so Cassini's mission ended in 2017, excuse me. But since that time, we've actually been able to observe Enceladus with the James Webb Space Telescope and confirmed that the plume is still there. This is something that's exciting for potential future missions, that the longevity of the plume seems to be, decades at the very least, based on the fact that the E-ring is there. It's likely much, much longer than that. And so this means that a future mission could be envisioned to go back and to sample that plume and be able to search for evidence of biosignatures. So there are a lot of different ways that we could explore Enceladus. We could do flyby or landed type missions. Indeed, the latest Planetary Science and Astrobiology Decadal Survey highlighted Enceladus as a future flagship to follow Uranus orbiter and probe. But there are also other ways that we might be able to get down through those cracks and access that ocean directly without the need to dig or drill. And that's what you can see in these blue arrows here. And so again, we at JPL like to dare mighty things. This is a 3D image based off of photoclinometry by Paul Schenk. It's a little bit exaggerated in the Z direction, but this gives you an idea of the slopes and the things that we might need to navigate on the surface. You sort of have to go up the crust before you can go down into the trough and access potentially that liquid water ocean through one of these tiger stripes. And we at JPL, who dare mighty things, have been developing a potential architecture, a robot that could do just that. So this is something that we refer to as the Exobiology Extant Life Surveyor. It is oh, hang on, let me mute that. Sorry. It is a snake-like robot that is designed to be able to not only handle a loose regolith at the surface, to be able to go up those steep slopes, but then go down into that icy conduit, push against the walls to be able to counteract those plume forces of gas and grain shooting up and be able to potentially access that liquid. So that was a video that was actually designed by one of the animators of the Avengers movies. It's fun to live in Los Angeles. It has some perks. But EELS, this is what it actually looks like. We've built a couple of prototypes at this stage. Now, there's something that's important to note here is that the one-way light time for communication between Earth and Enceladus can be anywhere from about 68 to 86 minutes one way. So that means that we can't remotely guide this with an operator on Earth. This robot has to be able to operate autonomously. And so because of that, it has autonomy built in to sensing payload of 3D imagers, LiDAR, and it's able to essentially sense its own environment and make its own decisions based on, some rules and some recommendations that we would provide for it. This allows it to adopt different gates to be able to move around or through different hazards and also to go down into that conduit. But of course, that looks all very well and good on paper. But now I'd like to show you some of the work that we've done just in the last 2.5 years to really get there. So this is one of our prototypes. You can see that it's got these counter-rotating fins that we can change out for different sizes depending on what sort of tests we run. This is us at the Pasadena Ice Rink. They allowed us to test on real ice at about 5 o'clock in the morning. We've also done tests here in our Mars yard to look at more loose, unconsolidated media like those plume grains that fall back down onto Enceladus' surface. And so this was meant to be able to test its capability to move, to be able to get out of being stuck, something that, for example, on Mars with the Spirit rover, we encountered, noticed that in very loose media that can be a challenge. Here you can see it navigating, doing path planning with its autonomous sensing payload and being able to make decisions. It can also raise its sensor head up quite high, depending on how many segments you allow to do that, to be able to get a higher bird's eye view of its surroundings and help generate that 3D map. Here you can see eels navigating a slope above 35 degrees. That is sort of one of the limits of traditional rovers, is that they can't go up very steep slopes. You can see here we were at one of the ski resorts nearby Los Angeles. So that was a series of testing that we did about a year and a half ago. And then last year, we were able to do our full range of testing of our final prototype up in Alberta, Canada. And this is a preliminary video. This was from a field test that we did just a few months ago. So we're still crunching on a lot of the data. Just to give you an idea of what it takes to bring a whole team of scientists, engineers, and multiple robots out to the field. So this is one of the robots we brought with us, which was meant to sense the forces that eels would experience as it's pushing against the walls of a conduit. So this one you can think of as like two EELS modules, but on each arm, sort of split in half. One of the reasons we selected this particular glacier, Athabasca Glacier, is because you can see these giant buses. This is a really accessible spot for us. It allowed us to move a lot of equipment and gear really easily to position us onto the glacier. But we did have to do some heli drops of a few pieces as well that you can see here. This was part of an extensive campaign of 3 weeks where we maintained some equipment on the glacier, but we ourselves did not camp on the glacier overnight. We stayed in a lodge nearby, but it allowed us to do all sorts of different testing on a realistic environment. We were able to have a whole host of things for horizontal mobility to see how the robot moves, how it deals with different combinations of terrain types that were challenging for us to simulate in our different test beds at JPL. And we also were able to test some, oh, yep, that's all the common luxuries of home. We're also able to test some of the vertical mobility as well, which let me skip forward just a bit and see if we can get to some of that later on in the video. So here you can see some of the crevasses and the conduits that we were exploring that we later did some testing with the robot. And you can see this is September, so the sun has been melting a lot of that glacier throughout the summer months. We still had a little bit of meltwater coming down on us, which again made the icy surface really slick and made it excellent for testing how well our robot could handle that slippage. Let's see if we have some better tests here. Here you can see we did some rigging to be able to position some of these robots in place so we could very carefully measure the forces of being able to push against the walls of the conduit and determine how much force was needed to be able to get a good grip and then be able to move up and down. And so we have a whole bunch of data that I mentioned. We collected a lot of LiDAR maps so we can ensure testing in silico later on of our autonomy. And so it was a really, really successful test. And I do also want to highlight quickly that our safety team was super important. A lot of these moulins, these areas where we were testing these glaciers, they go, or these robots in this glacier, they go down very, very deep. It can be quite dangerous. And so for each of our 2 scientists or engineers, we had 1 safety person. And so that was really beneficial for us to be able to, as you can see, navigate these really treacherous areas and do so safely. So this is another artist concept of what a future EELS robot might look like on a world like Enceladus, potentially bringing back evidence or transmitting back evidence of life, maybe as we know it, maybe as we don't know it. But this is one of our motivators for all of these mobility platforms that we're developing. This came from Carl Sagan and the very first landers we ever sent to Mars, and how incredibly, amazing those missions were, but also incredibly frustrating because we couldn't move. What if life was just behind that rock, just out of reach of your robotic arm? And that's what mobility gets us, is access to these hard to reach places. That's something that was definitely high on our minds as we've been developing this EELS concept, as well as other robotic explorers to help us understand the potential for life in our own cosmic backyard. And so with that, I'd like to thank, of course, all of the things I've spoken about are massive, massive teams, far too large to list here. But just I'm incredibly grateful for all of them. And I would like to thank you for your attention, and I'm happy to take any questions you might have. All right, I see one in the chat. Okay, this
Yeah.
one's from Katerina Yokum. How can early career scientists/engineers get involved with future ocean worlds missions such as EELS? That is a great question. There are a lot of different ways to get involved. Let's start with the most recent one that's coming and then get to the ones that are a little further on the horizon. So for the Europa Clipper mission that is launching next year, and it's likely that there will be a not a guest investigator, a participating scientist program. When it comes to funding, I think there are certain opportunities that are open through NASA, but there also will likely be some opportunities open through ESA. And so I would encourage you to look and see what sort of ways might exist for you to be able to write a proposal and join the team as a scientist. That being said, there are always tremendous opportunities for students to get involved with either doing internships or doing a postdoc under someone who's a co-investigator on that mission. And there are similar opportunities for Dragonfly. Though that one's going to launch presumably in about 2027, 2028, and land in 2034. Remember, space is big. But again, that should have some similar opportunities for being involved through writing proposals or joining as a potential intern. There's also a guest investigator program, which has been really great for getting early career students involved who typically have not been involved or had access to any sort of planetary science mission experience before. So I would encourage you to look through your institution, check out what kind of ESA opportunities might exist. And I should point out for Europa Clipper that JUICE, that mission is going to arrive at about the same time. And so there are going to be a lot of synergies between those two missions. So see if you can get involved through JUICE as well. For farther future mission concepts like EELS, we're of course going to continue to develop that technology, but it may be until the next decade or so when that really starts to take off and potentially become a real mission, as it were. Right now, it's been mission to Enceladus has been recommended by the Decadal Survey. This is what provides recommendations to NASA, and then NASA decides whether or not to implement those. And certainly, there's a lot of support within the science community, and so I think as long as we continue to develop the technology to enable exploration of those worlds, that'll be something on the future we can look forward to. Let's see. I'd like to
There
know
are
your
two more
opinion.
folks.
Oh, go ahead, Wolf. Sorry.
There are two more questions at the chat. Yes.
Yeah, I see one from Antonio. I'd like to know your opinion about the type of organics you're expecting to find in the dunes. Great question, Antonio. So, we have some measurements of Titan's atmosphere and a few measurements from the ESA's contribution to Cassini, the Huygens probe that landed on Titan back in, oh gosh, was it 2004, 2005? But that spectrometer, again, wasn't designed to detect these super complex organic molecules. Measurements from the surface by Cassini Sears tell us that there are very, very high mass organics, but we can't distinguish exactly what they are. Essentially, if you were to look at a mass spectrum, you would just see a forest of peaks. And so the instruments that are designed to be part of Dragonfly's payload are tuned to in a similar way to how we look at proteins, right? Proteomics, things like that, where we have really complex large organic molecules. That's why the laser desorption mass spectrometer is part of the DRAMS, the Dragonfly mass spec instrument, to be able to carefully ionize and volatilize those organic molecules without busting them apart, so that we can be better at identifying what they are. Now, in the lab here on Earth, we've been doing all sorts of experiments to see if we can replicate what we currently understand to be the physical properties and the grain sizes and things like that that we've observed on Titan, so that we can better inform those measurements. And we have some ideas. We think that, these may be rich in compounds like hydrogen cyanide, acetylene, some primary amines, and some other sort of carbon, hydrogen, nitrogen rich molecules with maybe a little bit of oxygen incorporated in them as well. So that work is going to continue, and I'd certainly encourage you, if you're interested in lab work, there are a ton of combinations and different mixtures that we haven't tried yet. Okay, let's see, from Teresa Margari, is there any future mission designed to send a lander or snake onto the Ganymede surface? I know there are a lot of concepts that are under development. Ganymede, of course, is another ocean world, very excellently pointed out by Teresa here. This one is really large, right? This is the largest moon in our solar system. And so presumably that liquid water ocean may have been around for a while. Ganymede is a unique case, or a more unique, more similar to Titan in one respect, because its ocean, we think there may be a layer of high pressure ice down at the seafloor. So it's the ocean liquid we think is sandwiched between two different water ice layers. Now, that doesn't mean that it's not a habitable ocean, but it may mean that exchange between that liquid water ocean and the rocky interior, where some of the sort of chemical energy might be stored, some of that may just take longer. And so it's certainly an interesting place to study. I know concepts have been proposed, and I think that that would be something to keep an eye on in the future. Timothy is asking, which location do you think is most likely to have bacterial or other life? Well, it's a combination of which one is likely to host life, and then which one do we have any hope of actually detecting, right? It's both of those things together that really motivate my thoughts on where we might go next. That's why I'm so excited to be a part of this Titan mission, because it's got such, the Dragonfly mission has such, uh, Titan has such, complex organic chemistry happening on the surface, and there are places on Titan's surface where it looks like we may have had cryovolcanic activity, or some place where stuff from the interior, from that ocean, might have spewed out onto the surface. So that's important to study there, to understand sort of the prebiotic context, and then maybe get some ocean materials. Europa, of course, has a lot of these chaos terrains, these places where it looks like there could have been exchange. And the powerful payload of Europa Clipper is sensitive to certain kinds of organic molecules and certain biomarkers, if indeed they're there. At high enough concentrations, we could see them. But EELS, I think, is unique because it, instead of waiting for that material to come to us, we could go to the ocean. And if you can access a liquid water ocean, the real key advantage in my mind that opens up is now you can do concentration. You can do filtration, say with a very small filter to get any, if there are microbes, you could concentrate those. You can do supercritical water extraction or something like that on like large volumes of liquid that you're just sucking in, say with a tube, with a straw, and really get like multiple orders of magnitude concentrated potential biosignatures if they're there. And so that gives you a better advantage of saying, even if something is trace, even if the life is dilute in that ocean, we would have a better chance of seeing it. And so I think that's a key advantage that in situ missions like EELS, concepts like EELS, could have. And do we have an idea from Evangelia of how Enceladus plumes change with time? Yes, we do. Because Cassini was in the Saturn system for 13 years, that's about half of Saturn's orbit around the sun. Saturn's orbit is 29 and a half years. Space is big, and Saturn is way out there. And so we know for about half of the seasons on Enceladus and Titan, the moons of Saturn, we know the behavior, and we do see some periodicity associated with that orbit, as well as Enceladus's 33-hour orbit around Saturn. But the plume is sustained during that time. The overall flux may vary, but it never turns on and off, for example. Now, certain parts of those cracks, there are two models. One says that it's just diffuse eruption along the entire fissure. Another model says, no, there are 100 discrete jets that are at specific points, spaced about 5 kilometers apart along each fissure. in reality, it's probably a combination of both. And while we may see certain areas during Enceladus's orbital period kind of get more intense or less intense, what we would target for something like EELS, a future mission concept, would be to go to one of those areas of peak flux where it doesn't seem to fluctuate that much, and that would be the spot that we would ideally go down. But there's a lot of work to do. We need a lot of very smart scientists and engineers to help us do that. So hopefully those of you who aren't involved in astrobiology or planetary science who want to be will join us, because there are a lot of exciting places to explore in the solar system.